the audience to do the questions in the chat, and I will then, when you finish, I will give you the questions.
Okay.
So now I will present Professor Shirota. Professor Shirota was proposed as invited speaker to the organizing committee of the 23rd SINAQO by Professor Juana Chesa de Silva from the National University of Rio Cuarto. Professor Shirota obtained his PhD degree in 1998 from the Graduate University for Advanced Studies, Department of Structural Molecular Science, Institute for Molecular Science, Okazaki, Japan. From 2000 to 2003, he was appointed research assistant at the University of Tokyo, Department of General Systems Science, and from 2003 to 2006, he was research associate in the State University of New Jersey, Rutgers, Department of Chemistry and Chemical Biology. Since 2006, he has been associate professor in the Department of Chemistry, ChibaUniversity, Japan. Professor Shirota's research interests are related to the study of liquid properties and molecular dynamics in liquid and solutions using laser spectroscopy. In addition, he is a leading scientist in the field of synthesis and characterization of novel liquid materials. The result of his contributions are reported in more than 78 high-impact publications in peer-reviewed international journals and 2 book chapters, with an H index of 40 and over 4,200 citations. Professor Shirota also received several prestigious awards, including the 2019 Academic Award from the Japan Association of Solution Chemistry. Today, he will be presenting his talk entitled Heavy Atom Substitution Effects on Liquid Properties of Ionic Liquids. Thank you so much, Professor Shirota, for giving this talk.
Thank you very much for the kind introduction. I'm very sorry about this, but at last I can reach you. Anyway, at first I would like to thank the organizers for giving me a great opportunity to give a talk in this historic symposium. I'm very happy to present our work here. I would also like to thank my friend, Professor Dario Falcon, to introduce me this symposium. Thank you. So today, I will talk about heavy atom substitution effects on liquid properties of ionic liquids. In particular, I would like to focus on sulfur-containing houstonium-based ionic liquids. So ionic liquids. Ionic liquids are molten salts at room temperature. So ionic liquids include both the natures of salts and liquids. However, ionic liquids are somewhat strange. For example, the salts show very low melting point. Common salts, such as sodium chloride, show very, very high melting point. So it is something strange. Ionic liquids are also strange liquids. Here I'm showing 2 photos. We can burn ethanol very easily, but in the case of ionic liquids, even they consist of purely organic cations and anions, we cannot burn by a simple torch easily. So this means that ionic liquids are actually show almost negligible vapor pressure at room temperature and pressure. This feature is really strange for liquids. Here I'm showing a simplified view of the origin of lowering the melting point of ionic liquid. In the case of sodium chloride, the stable point is very, very deep because they are compact and spherical, so they can reach each other very closely. However, common ionic liquids have a bulky cutout, something like this. In this case, stable point goes to the longer distance between cation and anion due to the repulsion force. So the potential energy surface around the minimum is very, very shallow. Therefore, ionic liquid can move at very low temperature compared to rock salt or common salt. Most of ionic liquid cations are composed of non-polar part and ionic part. In a sense, ionic liquids are somewhat a kind of surfactant, so they show amphiphilic nature. In fact, this feature provides a strange structure in liquid. Here I'm showing MD simulation snapshot of butyl-imidazole hexafluorophosphate calculated by Canongia Lopez and co-workers. Green part denotes alkyl groups, but red part denotes anions and imidazole rings. So we can clearly see the segregation structure. So in fact, this feature provides high solubilities for ionic species and non-polar and polar solids. So ionic liquids are really good solvents. Experimentally, Alessandro Toriolo and co-workers observed the evidence of segregation structure of ionic liquids. They demonstrated an excellent study by X-ray diffraction. According to this report, the longer alkyl group of imidazole cation showed the stronger scattering intensity and the larger scattering species in the Q region, in the low Q region. So they attribute these scatterings are coming from the domain part of non-polar region, non-polar part. So these unique features of ionic liquids, such as low melting point, negligible vapor pressure, and microsegregation structure, are coming from a kind of complex intermolecular interactions. But at the same time, intermolecular interaction is a kind of key to understand the nature of ionic liquid. Here I'm showing the typical cations and anions for ionic liquids. Most of cations are organic ions, such as imidazole, pyridinium, ammonium, phosphonium, and pyrrolidinium. Common anions include both inorganic and organic ions for ionic liquid, such as halides, nitrate, tetrafluoroborate, hexafluorophosphate, acetate, dicyanoamide, bis-toluolomethylsulfonylamide. Hereafter I simply call NTF2. Actually, this anion is one of the most popular anions for ionic liquid because this anion is electrochemically stable and this anion shows the lower melting point and glass transition point. Both the physical and chemical properties of ionic liquids are tunable. There are two major methods to control the ionic liquid properties. One is exchange, the combination of cation and anion. As I showed, there are so many cations and anions, so we can choose the combination of cation and anion as we like. Another one is more chemical method, namely organic synthesis method. In this case, as I showed, most of cations are organic ions. Therefore, we can make more finer control or final design of cations by using organic synthesis method. Here I'm showing examples of tunability of property in ionic liquid. When we use this cation with NTF2 anion, viscosity is shown like 70 centipours at room temperature. However, when we substitute this anion by PF6 or ASF6, viscosity goes up like 10 times higher than that of NTF2 salt. And next one is the synthesis method. We exchange the alkyl group by ether group. Viscosity goes down substantially, but surface tension doesn't change much. About 15 years back, we synthesized silicon substituted imidazoline-based ionic liquid. The idea was very simple. Because polysiloxane is very flexible and show very low glass transition temperature and melting point, we thought silicon works for ionic liquid as well as polymer. So we synthesized like these ionic liquid. Also, the comparable carbon substituted ionic liquid to understand the effect of silicon. So the viscosity of silicon substituted ionic liquid are lower than that of respective carbon substituted imidazoline-based ionic liquid. So silicon works to reduce the viscosity in ionic liquid. However, it is well known that boiling point and shear viscosity increases with heavy atom substitution in molecular liquid. For example, here I'm showing the boiling point of methane, and when we substitute carbon by silicon, boiling point increases. Further, germanium, tin, they show much higher boiling point. Shear viscosity of chloroform is much higher than chloroform. Similarly, GHL2O ether shows higher viscosity than GHL ether. So, in fact, this feature is coming from the stronger intermolecular interaction by dispersed force by heavy atom substitution, because heavy atom substitution gives larger molecular volume. So, van der Waals interaction goes increases. So, however, as I showed, viscosity in ionic liquid shows opposite heavy atom substitution effect. Namely, heavy atom substitution gives a lower viscosity. We further tested the case of anion. In this study, we compared hexafluorophosphate, hexafluoroalcinate, and hexafluoroantimonate. Viscosity goes down and down, we observed. So, in the case of imidazoline-based ionic liquid, whatever their cation or anion, we can observe clearly the reduction in viscosity by heavy atom substitution. In fact, this is also true for non-aromatic cation-based ionic liquid. Here I'm comparing ammonium and phosphonium cation-based ionic liquid with the same groups and same anion. So phosphonium-based ionic liquid show much lower viscosity than ammonium-based ionic liquid. And we also compared hexafluorophosphate and hexafluoroalcinate. So in this case, we can also see the reduction in viscosity for both cation and anion cases. In dual substitution for this ionic liquid, we observe a kind of product of cation's effect and anion's effect. So in a sense, it is not enhanced effect, but looks like just product effect. Anyway, whatever ions are aromatic or non-aromatic or cation or anion, usually heavy atom substitution works to reduce the viscosity in ionic liquid. So why is that? Here is our scenario. When we substitute a lighter atom by a heavier atom in the same group, the distance becomes longer due to the repulsive force coming from the larger ion volume. So the minimum point shifts to the longer distance and potential minimum becomes shallower. Therefore, intermolecular interaction becomes lower. As a result, the viscosity is reducing. Please note that this is for the ionic liquid case, but in the case of neutral molecular liquid, the heavy atom substitution effect works for opposite side, namely heavier atom substituted molecular liquid shows a higher viscosity due to the increase in the intermolecular interaction via van der Waals interaction. Okay, so several years back, we focused on sulfur containing phosphonium-based ionic liquid because sulfur is non-metallic and multivalent. Therefore, sulfur is included in a wide variety of organic and inorganic compounds. Working hypothesis was sulfur should work better for viscosity than oxygen, namely ether. In fact, Fay et al. Already demonstrated this, namely for imidazole-based ionic liquid, sulfur-containing one shows lower viscosity than ether group substituted cation-based ionic liquid. So we believe this should work for phosphonium-based ionic liquid. In addition, there was no report on the phosphonium-based ionic liquid whose cation include sulfur. So this is another motivation to study this in that time. So here I'm showing a new family of sulfur-containing phosphonium-based ionic liquid. We synthesize very simple cases like methyl-thio-methyl group, methyl-thio-ethyl group, and ethyl-thio-ethyl group with the tolyethyl phosphonium cation and tolybutyl phosphonium cation. But in this talk, I would like to focus on this cation to understand effect of sulfur. So we want to compare. I want to compare sulfur, oxygen, and carbon. In fact, liquid density shows the rather boring tendency, namely sulfur substituted ionic liquid shows the highest, and alkyl group substituted one is the lowest. We were very shocked about the result of viscosity because sulfur substituted phosphonium-based ionic liquid shows the highest viscosity among these three ionic liquids. And also, we found that somewhat surface tension of sulfur substituted ionic liquid is higher than these two ionic liquids. So, why sulfur substituted phosphonium-based ionic liquid shows the opposite heavy atom substitution effect on the viscosity compared to common ionic liquid. At the moment, we speculate that because this cation has short ethyl groups, this site can access to anion without the perturbation by heavy atom substitution in the side group. Instead, this part increases the interaction by a stronger van der Waals interaction. As a result, viscosity goes up. This should be also influence the surface tension because surface tension of sulfur substituted ionic liquid is higher than that of ether group and alkyl group substituted ionic liquid. We further examine the intermolecular vibrations in the three ionic liquids. In our group, we focus on intermolecular vibration in ionic liquids as well as liquids and solutions to understand the molecular level of aspects in condensed phase. This is because the intermolecular interaction is well influenced by the intermolecular vibration. So, in a sense, intermolecular vibration probes the microscopic structure and interaction. Our expertise is femtosecond Raman-induced K-effect spectroscopy. Hereafter, I simply call femtosecond light case, which observes the polarizability response. A complementary method is Terahertz time domain spectroscopy, which observes the dipole response. Now, I will show you the results of both spectroscopic measurements. In fact, this experiment was made at Kobe University, Professor Kei Tominaga's group. Before I show you the result, let me show you why femtosecond light case is so good at observing the low frequency motions in condensed phase. In the case of steady-state Raman spectrometer, it is very hard to distinguish the low-frequency Raman scattering and Rayleigh scattering because the wavelengths of the two scatterings are quite similar. Further, Rayleigh scattering has a strong intensity, so it is very hard to distinguish between them. However, if we use time domain spectroscopy, like femtosecond light case, we can avoid this problem. There are two key points. First one is femtosecond laser pulse. Because femtosecond pulse is very short in time and electric field is very high, femtosecond pulse induces the vibration coherence of the Raman active mode within the spectral width of the laser pulse. Then we use probe pulse to get the signal at a certain time. We sweep probe pulse relative to point pulse to get time domain data. The time domain data is converted to frequency domain data, namely spectrum, by a Fourier transform. Actually, the second key point is Fourier transform. Because Rayleigh scattering is zero wave number shift, so this signal is just background in time domain data. Therefore, before we subtract the background from the time domain data, we can obtain the low frequency spectrum without the contribution of Rayleigh scattering. Now here I'm showing the low frequency spectrum, low frequency Raman spectra of these three phosphonium based ionic liquid. We can clearly see the peak at about 20 wave number for the three ionic liquids. And this peak shifts to the lower frequency side with increasing temperature. This feature is rather general because the intermolecular interaction becomes weaker by heating up the sample. How about terahertz spectrum, which is a far-infrared absorption spectrum? The peak was observed at about 70 wave number, and the peak shifts to the lower frequency side. So again, intermolecular interaction becomes weaker with increasing the heat, increasing the temperature. However, what is the difference between the peak frequencies of the two ionic liquids, of the two different spectra? We thought these are coming from the different species, namely polarizability and dipole. So we calculated the polarizability anisotropy and dipole moment of the 4 ion species. What we found is that this anion has almost 0 dipole moment. Therefore, in IR spectra, this anion cannot contribute to the spectral density much. On the other hand, Raman spectra includes both the contributions of cation and anion because the polarizability anisotropy relatively close each other. So now let's consider about the difference between sulfur, oxygen, and carbon. The intermolecular vibration is not that simple like harmonic oscillator, but harmonic oscillator is a good measure to understand their vibrational nature. So we calculated the first moment of the low frequency spectrum, which is almost the center frequency of the broad spectral band. Femtosecond latest results showed that sulfur-containing ionic liquid is the highest first moment, but ether group substituted ionic liquid showed the lowest first moment. In fact, this trend is well correlated with viscosity data. Actually, this is pretty reasonable because the sulfur increases the intermolecular interaction. As a result, intermolecular vibration intermolecular vibration is reflected by the stronger intermolecular interaction. However, why terahertz TDS or IR spectrum didn't show that kind of correlation? At the moment, we think polarizability seems to be a dominant factor for the heavy atom substitution on the viscosity because this effect is coming from the van der Waals interaction. Okay, now let me summarize this talk. Today we reviewed heavy atom substitution effects on ionic liquids, especially on the viscosity. And I showed you results of sulfur-containing phosphonium-based ionic liquids and unique features in viscosity and surface tension were observed compared to oxygen and carbon substitute phosphonium-based ionic liquid. Polarizability response correlates well with viscosity for these three substituted phosphonium-based ionic liquid. And here is my co-author in this talk, my student, Masa Ando. And I would like to thank also the former student, Mr. Takahashi and Kachinuma. And I would also like to thank Professor Kaoru Ota and Kei Tominaga from Kobe University to measure the terahertz TDS spectrum. The works were supported by JSP's Kakenhi and Takahashi Foundation and Malvern Foundation. I will also thank Kobe University Molecular Photoscience Research Center to support our collaboration work with Professor Kei Tominaga's group. And thank you very much for your kind attention.
Thank you very much, Professor Shirota, for your excellent presentation. Now we have time for some questions. The first one is from Fabrizio Bisogno in the Zoom chat, and he says, very interesting work, Professor. I wonder if selenium substitution may behave following this trend. Do you have any study on that?
Sorry, say it again, please.
Yes, he says that it's a very interesting work, and he wonders if selenium substitution may behave following this trend. Do you have any study on that?
No, I've never studied yet, but selenium should work, but I'm not, at the moment, if you want to reduce viscosity, selenium should work in gasoline-based ionic liquid, but I doubt in the case of phosphonium-based ionic liquid, as I showed. Thank you.
Perfect. We have another question from Dario Falcone. He says, very interesting talk. Can infer other properties such as electron donor capacity of the ILS by Reichs?
Sorry.
I can read it again. Can infer other properties such as electron donor capacity of the ionic liquids by Reichs?
Not very sure. I never tried, but could be interesting. Yeah.
And we have one last question. From Alejandro Fracaroli. You have compared the different ionic liquids in terms of their viscosity in relationship to their composition. Are there any difference in terms of their stability or biodegradation upon tuning the anions and cations and introducing heavy atoms?
Usually, I forgot exactly, but this really depends on the cation and the anion. Some shows very high stability, but sometimes not. In particular, halide case shows not so high stability. And also hexafluorophosphate also shows relatively bad stability, especially with water, something like this.
Thank you very much. So if we don't have any more questions, you can still ask Professor Shirota questions through the chat or via mail. And once again, thank you very much, Professor Shirota, for your excellent talk.